Okay, good morning. Before Gordon starts, let me make a couple of announcements. First of all, you saw there is a collection of books. In particular, there's several books from series Ensaios Matemáticos of Brazilian Mathematical Society, and that means memoirs somehow could be translated. So we already receiving a lot of requests for these books. So first of all, let me present Maria Eulalia Vara. She is chief editor of this nice collection, and she's putting a lot of effort that this series keeps going on. And first of all these books are available for free online. So you received in your backpacks some folder of Ensaios Matemáticos, so you can download them for free. Also, these books are very cheap. So if you are willing to have real book copy, there are also instructions how to buy them online, and Brazilian Mathematical Society would send them to you. So they also donated of each volume seven books, which we will distribute randomly at the last day for last survivors of this meeting. And please visit the site of the book, and Maria Eulalia, thank you very much for keeping this going on. Okay, next thing to announce. So please be careful walking around in the evening. So yesterday we had late night, some not pleasant incidents, so just watch around. And it's something surprising for this area, but probably we are here for too long. And okay, next announcement for tomorrow night. We thought how to substitute official dinner because it would be too big. So there is one place, maybe some of you already visited, it's called Lapa 40. I don't know this place myself. Yeah, Lapa 40, it's a kind of dance and show place. So tomorrow evening they will have, at the beginning, around from 10 to 11:30, some show of samba. I don't know what exactly they have in mind, and then afterwards there will be dance party until last dancer leaves. So everyone who is interested to go to this party, we conference organizers are supporting this, so just leave your name to the secretary. So you will get a free ticket to this show and then to stay there. So don't forget, it's after 3 o'clock. Please leave your name there. So for us, just to know how many people are willing to go to this place, and I think that's all for now. So,
okay. Is it turned on? Yeah. Today I want to talk about the lace expansion for self-avoiding walks. Actually, what I have to say will continue into tomorrow as well. So tomorrow's lecture will depend on today's lecture. I guess this information is more useful for the people who aren't here rather than the people who are here, but that's the way it will be. And well, the lace expansion started in 1985 with a paper by Bridges and Spencer. Who applied it to study weakly self-avoiding walk in dimensions greater than 4 and proved that the mean square displacement is asymptotically linear in the number of steps. Subsequently, there's been a lot of development. There have been many dozens of papers have been written that use the lace expansion and apply it to various other models, including percolation and contact process and easing model and other things as well. If I have time at the end of tomorrow, I'll give you a little bit of a survey of what type of results have been obtained. But really my goal is to try to present the method in its simplest possible setting and to try to prove a theorem for you that will give you kind of the essence of what the method is. So the theorem I would like to prove for you, I won't, but I'll state it here. So this is a theorem that Hera and I proved many years ago, now in 1992. So it's for the nearest neighbor self-avoiding walk in dimensions d greater than or equal to 5. It says that the number of n-step self-avoiding walks is some positive constant a times mu to the n times 1 plus smaller order term. So this is saying that the critical exponent gamma is equal to 1. There's no polynomial correction to leading order. So the number of n-step self-avoiding walks is growing purely exponentially to leading order. And the mean square displacement, this is for the strictly self-avoiding walk, is linear in the number of steps to leading order. So there's some positive constant d. Actually, d is strictly greater than 1. So if we were talking about simple random walk, the mean square displacement, just the variance of the endpoint, would be exactly equal to n. Here what happens is that the power is n to the 1, but there's a constant in front which is strictly greater than 1, which is showing the effect of the repulsion of the walk. It's being pushed away from the origin faster than simple random walk, but only at the level of the constant and not at the level of the exponent, as should be the case in lower dimensions. So this is a statement that nu is a half. The power 1 here is 2 times nu. And you can say more. You can say that if you take the position of the walk at time nt, where t is some positive real number, and divide by the square root of d times n, then this converges in distribution to Brownian motion. And since I also talked about the other critical exponent eta in the first lecture, I should mention a more recent result of Hera in 2008 that says that the critical 2-point function, so ZC is 1 over mu, this critical 2-point function is equal to some constant divided by x to the d minus 2 times higher order terms. So this is a fairly complete description of what's going on in dimensions 5 and higher. This is the statement that eta is equal to 0. The proof uses an expansion method, and expansions require small parameters in order to converge. And the small parameter, as we'll see, is essentially the inverse dimension, or actually it's 1 over the dimension minus 4. And when d is equal to 5, that's not so small. And so proving convergence of the expansion in this setup for the nearest neighbor model is pretty tricky and actually required a computer assistant proof and lots of estimates that you don't want to look at. So I'm not going to talk about the proof of this. I want to set a more modest goal, which still shows you what's going on in the method. And what I want to show you is this. So here's our goal for today and tomorrow. I want to consider the susceptibility, which is just the generating function for the number of n-step walks. And instead of proving that Cn is growing purely exponentially, what I want to do is show that the approach to the critical value Zc of the susceptibility diverges linearly. And I won't show such a strong asymptotic statement as what you see here, but just upper and lower bounds. So 1 over 1 minus z over zc to the power gamma equals 1. The power there is just the first power. That's the critical exponent gamma in a different guise, an easier one to get at, the generating function, than actually to study the coefficients in the generating function. So this is as z approaches zc. That's the goal. And I'm going to relax this hypothesis here to make our job easier. So in 2 settings, we'll do them simultaneously. So the settings will be that we'll look at the nearest neighbor model for d greater than or equal to some dimension d naught, which is actually a lot bigger than 4. As I said, there's a small parameter, which is 1 over d minus 4. And the smaller it is, the happier you are in trying to carry out the proof. And so let's be happy and take d minus 4 to be very large. Historically, this is actually the way that things proceeded. First, the proof came in this setting, and then it was the d naught was reduced to 5. But this 4 is special. It is the upper critical dimension for the self-avoiding walk. There's various sort of heuristic ways that you can see that that should be the case. One is that the Hausdorff dimension of a Brownian motion path is equal to 2. And two two-dimensional objects generically don't intersect each other in dimensions bigger than 4. And so this is supposed to give you some feeling that two simple random walks don't want to intersect themselves anyway in more than 4 dimensions. And so if you're extending a long simple random walk, telling it to be self-avoiding isn't going to change its behavior. So that's one way to see d equals 4. Another way is to ask, what is the expected number of intersections of two independent simple random walks? That will be infinite in dimensions 4 and lower, but it'll be finite in dimensions higher. I'm talking about infinitely long simple random walks here. So again, 4 comes in as some kind of a critical dimension for the behavior of intersection properties of random walks. And this is the 4 that we're staying above here. And so I'd like, in what we're doing today and tomorrow, to see this d greater than 4 actually popping out. And you don't see it here. So I'm going to insert a small parameter in another way, which is to consider the spread out model. So the spread out model we defined in the first lecture. So this is just a model where the possible steps are wherever you are now, you're allowed to step to any point which is in a box of radius L, centered at your current position. Okay, so we're increasing the degree of the graph by doing this. We're making it have order L to the d instead of 2d, if L is the radius of the box. And that's a good parameter to make the expansion converge. So we're going to take L greater than or equal to some number that depends on the dimension much greater than 1, and d greater than 4. So here you really see the critical dimension popping out, and so that's why I want to consider this case as well. But in the proof, we're only going to notice the difference between these two models in one place. Maybe we won't see it today. Now, to prove to achieve our goal, so this is the only thing that we're going to be proving over the next 2 classes, I'm going to make use of a differential inequality. This is a differential inequality for the susceptibility, for chi of z. It was proved by Bouvier, Felder, and Fröhlich. In 1984. Around that time, there were differential inequalities of a similar nature that were showing up in different contexts as well. One well-known one is the paper of Eisenman and Newman on the triangle condition for percolation, which also arose in a differential inequality for the susceptibility or the expected cluster size in percolation. It was showing up also in spin systems. And the way that it works in the self-avoiding walk model is like this. Actually, our job is pretty easy in one sense, in that we only have to prove one part of this one inequality here, because the lower bound comes for free. So before we come to the differential inequality, let's just observe something that we already know, which is that Cn is greater than or equal to mu to the n. This was something that came out of subadditivity. It's free from subadditivity, that Cn is greater than or equal to mu to the n. And so that implies that chi of z is greater than or equal to the sum of a geometric series with ratio mu z. So that's 1 over 1 minus mu z. And mu is 1 over zc. So the lower bound is free and holds in all dimensions. And what we're interested in doing is proving the upper bound. And it's the upper bound that is obtained with the help of the differential inequality. So what the differential inequality will give us is that if you, once you integrate it, is that chi is bounded above by something called b of zc. This has got nothing to do with the bridges. There was a b of z last time. This is a different b, divided by 1 minus z over zc, where b of z I'm interested in b as a function of z, actually, not just at the value zc, is what's called the bubble diagram. And it's just the L2 norm squared of the 2-point function. And the reason why it's called the bubble diagram is that in a Feynman diagram notation, you would draw this as a bubble tied down at the 0 with this vertex summed over the lattice, and each line in the diagram is representing a 2-point function, gz of x. So this is the bubble diagram. In percolation, there's a triangle diagram. If you look at lattice trees or lattice animals, there's a square diagram that comes into play. The bubble diagram also shows up in the Ising model. So these diagrams are not unique to this setting. And what is appearing here is the critical bubble diagram. So what we need to do is to show that that b of zc is finite in order to get a meaningful bound here. It won't be finite in all dimensions, actually. And it's not so easy to show that it's finite because, in fact, in dimensions 2, 3, and 4, and well, before these lace expansion methods came around, it was not possible to show that the critical 2-point function was finite for any x. So it wasn't known that any term in this sum was finite. And so that's kind of a more fundamental question than whether the series converges. So it's not obvious how this is going to work, but our first goal is to demonstrate this inequality. And here's this upper bound follows by integrating a differential inequality. And that differential inequality is what I'll call di. The derivative with respect to z of z times chi is bounded below by b of z, by chi of z divided by b of z. And if we make the denominator bigger, we'll make this smaller, so that's bounded below by chi of z over b of zc. So if you just integrate this differential inequality from z to zc, and make use of the fact that the susceptibility is infinite at zc because of this bound, then you will be led to this. So this is a calculus exercise to go from the differential inequality to the upper bound, and I won't do that exercise here. Chi squared, thank you. That's important. But I would like to show you the proof of this differential inequality. So let's start with the left-hand side and write down the derivative that we want to estimate. Chi, of course, is just a power series with coefficients Cn. So when we multiply by z, we boost the power up to n minus 1. When we differentiate, we bring it down. And so this is equal to the sum from n equals 0 to infinity of n plus 1 times Cn times z to the n. Or maybe n equals 1. And I want to represent this by a picture. So I want to think about a self-avoiding walk as being represented by a line. And so chi I would represent by this line. We're just summing over all the self-avoiding walks of any length that start at 0, and we're weighting by z to the length of the walk. But now this n plus 1 is counting the vertices along the walk. And so I want to represent that diagrammatically by putting a vertex on there, which you can think about as floating around anywhere it wants to on the walk. And basically what we do is we have a self-avoiding walk of a certain length, and then we stick onto the end of it a self-avoiding walk of some length, and we sum over all of those lengths. But the key thing is that really there's only one underlying self-avoiding walk, and so if I label these two pieces of the walk by 1 and 2, then I'm going to write here a little bracket 1, 2, which is to remind us that those two pieces of the walk have to avoid each other. All right, so this is my picture of this series. Now, chi squared, the picture for chi squared would be the same picture but without the little bracket 1 and 2. Chi squared would correspond to allowing the two pieces of the walk to intersect each other. And I'm looking for chi squared. So I'm going to say this is equal to this term which is just chi squared, without any interaction between the two pieces, this is inclusion, exclusion. So I'm including too much now by allowing the two pieces of the walk to intersect each other. So now I have to exclude the terms where they do intersect, because I don't want them on the left-hand side, and I've included them in this term. So those terms are going to look like this. We'll start at 0, do our first walk, and then do the second walk, and it has to intersect. And then it goes off and does whatever it wants. Now, in order to sort of not overcount, I'm going to focus on the last time that the second walk hits the first. That will give me an identity. I'll be subtracting the intersections in exactly the right way. But there's lots of different kinds of mutual intersections that are, or mutual avoidances that are going on here. For example, this 1, 2 was initially the walk 1, and it was a self-avoiding walk. So 1 has to avoid 2. And this walk 3, 4 was the walk 2, and it was a self-avoiding walk. So 3 has to avoid 4. But I've also said that the last time that the walk 3, 4 hits 1, 2 is this time. So that means that walk 4 is not allowed to hit 1, 2 at all. So there's going to be a 1, 4 and a 2, 4. So what this list is telling me is that walk 1 has to avoid walk 2, walk 3 has to avoid walk 4, 1 avoids 4, and 2 avoids 4. And with that list, this is an identity. It's just the inclusion-exclusion relation, taking into account the fact that I'm not allowing intersections between the two pieces here. I did allow them here, so I have to subtract off some stuff. Now, as an inequality, I would write this as I'm just going to forget about some of these. So if I forget about some of these, I'll make the subtracted term bigger. And the ones that I want to remember is just one, which is that walk 1 and 4 have to avoid each other, and then I don't care what else happens. Then, if you think about this in terms of generating functions, what this equation is, what this represents is chi squared minus, and let me call this term here q, the thing that I'm trying to get a lower bound for, this diagram where 1 and 2 intersect each other. That's what this is, 1 and 4, where they avoid each other, I should say. 1 and 4 have to avoid each other here. And so there's a factor of q from the part 1 and 4, and then there's a bubble for the bubble, the other two parts. So you can write out equations for these things. It takes a lot more blackboard space to write things in terms of equations, but the pictures are something that it's worth getting used to. And another thing that I can do a little better here, which is that something has to happen here. This bubble actually has to do something. And that is, I'm not including in here the term where the bubble shrinks to a single point. That corresponds to the term x equals 0 in the definition of the bubble diagram. And I can exclude that. Once I've excluded it, there's a plus q on the right-hand side, and there's a q over here. They cancel each other out, and this leads to the inequality that chi squared is less than or equal to q times b, which is what we wanted. Okay, so it's a sort of an elementary application of the inclusion-exclusion relation that leads to the differential inequality. And as I pointed out before, once you integrate the differential inequality, you end up with this. And we would have achieved our goal, which was to prove these, well, just the upper bound we need on chi, if we can show that the critical bubble diagram is finite. So the goal becomes show that B of ZC is finite in our settings, nearest neighbor model in very high dimensions, or a spread out model that's quite spread out in dimensions d greater than 4. And, well, this is where the lace expansion comes in. I'm going to describe, excuse me, I'm going to describe the lace expansion using the method of inclusion-exclusion. For self-avoiding walks, there are two approaches to the lace expansion. There's the method that was originally introduced by Bridges and Spencer that uses laces. If you want to know what laces are, I'm not going to tell you, but the tutorial this afternoon will be all about the lace version of the lace expansion. I'm instead going to talk about the method of inclusion-exclusion, which leads to the same conclusion, but it requires less formulas. Fewer formulas, but more pictures. So I'm going to be drawing more pictures of the type that you saw over there in the derivation of the differential inequality. So the conclusion of the lace expansion is going to be a formula. Yes? Yeah. It's the generating function for Cn of x. Because it's in the denominator. Bigger denominator makes a smaller fraction. B of zc is bigger than B of z. So Cn of x was the number of n-step self-avoiding walks that start at 0 and end at x. Gz, the two-point function, Gz of x is the generating function for that sequence. And it's going to play a crucial role in everything that we do. So what the lace expansion does is it produces an identity, an equation, for Cn of x, the coefficients in this two-point function that we're so interested in. And it looks like this. Cn of x is equal to the sum over y, C1 of y, times Cn minus 1 of x minus y. This is what you would have if you were just counting simple random walk paths. Right? If you're counting simple random walk paths that go from 0 to x, just condition on the position after the first step. There's C1 of y walks that will take you to that position after one step, y. And then you continue independently an n minus 1 step walk. What the lace expansion does is it tells you what the correction is. So you sum over all y, and you sum over all m from 2 up to n of some coefficient pi m of y times Cn minus m of x minus y. And the lace expansion provides a formula for this coefficient pi m of y that is capturing everything about the self-avoidance. It's telling you how different the self-avoiding walk is from the simple random walk, which is what the first term. If you put pi equals 0, then you have simple random walk. In fact, such an equation uniquely determines what these coefficients pi m of y is. So in a way, this is vacuous because you can, as we'll see later on, you can find a formula that tells you what these coefficients are in terms of this in a unique way. So there's always you can always write this equation. But what is useful about the expansion is that it tells you a nice form for what those coefficients are. All right, so let's see how it goes. It's going to be derivation by picture. So if you don't know what the pictures mean, you should ask me. So Cn of x, let's start with the left-hand side. This, of course, is for n greater than or equal to 1. So I'm thinking about a walk that actually goes from 0 to x in some number of steps. And I'm going to denote it by a line like that. What I'm trying to do is to produce a convolution equation for Cn of x. There's a convolution both in space and in time. You see here the time is being shared between two parts, two pieces, and here also the total time n is being shared between a pi and a self-avoiding walk. And also there's a convolution in space. So I'm looking for such a thing. And what we'll do is we'll just try to use inclusion-exclusion to compare with simple random walk, because this is a simple random walk contribution here. So let's pretend that we had this independence. That is, that we go from 0 to somewhere in one step, and then we carry on, and in our remaining n minus 1 steps go from wherever we were after our first step to x, so from y to x. But we no longer require this orange walk to avoid its starting position, well, the original starting position 0. So this is inclusion-exclusion. I'm including too much here because I'm including the situation where that orange walk passes through 0 and I don't want it. So what I should do is subtract off the configurations where the orange walk does pass through 0. So what this picture represents is the number of n-step walks that start at 0, end at x, and are self-avoiding, except they are required to return exactly once to the origin. Okay, the orange walk can only go back to the origin once because it's a self-avoiding walk itself. So I like the first term because the first term is exactly equal to the sum over y of c1 of y, cn minus 1 of y. And that's the first term that we're looking for, and so we're done with that part. The rest is going to give us the pi. Now, we're trying to have a convolution equation in which the number of some number of steps walks shows up. And unfortunately, that's not quite what we have here, because if I label this self-avoiding return to the origin by 1 and its continuation to x by 2, then unfortunately, well, it's just a fact that 1 and 2 have to avoid each other. The orange walk was a self-avoiding walk. And so I don't get a factor cn minus m 0, from 0 to x from that line because it's interacting with the self-avoiding return. So what we'll do is say that this number of walks is equal to the number of walks that you would get if you just forgot about the mutual avoidance between the self-avoiding return and the self-avoiding walk, the tail, with some correction. So there would be this. This is with 1, 2 avoiding each other. And then my orange chalk, this to x. So now this is supposed to represent, the different colors are supposed to represent a lack of interaction between the two pieces. But then I have to subtract off the contribution, the number of walks that you get where you do a self-avoiding return and then a self-avoiding walk, and the two actually intersect each other. Maybe they intersect each other many times. There will be a first intersection, though, in the term that I want to subtract off, and so I'm going to focus on that. And so there'll be a first intersection, and then it will go off to x. So this is the first intersection. First measured along the orange walk. So then, if I label these walks as 1, 2, 3, and 4, let's see who has to avoid whom here. So 1, 2, and 3 are all avoiding each other. 1 has to avoid 2 because that was a self-avoiding return. 3 has to avoid 1 and 2 because the intersection that we're focusing on is actually the first one along the orange walk, and so it has to avoid 1 and 2. 3 has to avoid 4 because that was a self-avoiding walk. The orange walk was self-avoiding, but 4 is allowed to intersect 1 and 2. All right, so this term is good because it's a convolution in time. There's no convolution in space yet, or it's of a trivial nature, but there's a convolution in time because there's a self-avoiding polygon here followed by an independent self-avoiding walk, and that orange line is going to give us a factor cn minus m of x minus y, with y actually equal to 0 in this case. All right, what about this term? So now we have a term that looks like this. I'll call it 1, 2, 3, 0, and 4 going off to x, and we have 1, 2, 3, 3, 4. So 3 and 4 have to avoid each other, and I would really prefer that they didn't have to avoid each other because I'm looking for this factor, Cn minus m of x minus y, which would correspond to a contribution from an n minus m step walk that went from y to x that was self-avoiding but wasn't interacting with the rest of the picture. And unfortunately, 4 is interacting with 3, so we're going to apply inclusion-exclusion to this term, the 3-4 interaction. So just forget about it. Then you would have this picture. 1, 2, 3 have to avoid each other, followed by a walk that goes off to x that's self-avoiding, but it doesn't care about that theta diagram, which is sitting beside it, minus a correction, and that correction is going to look like this. With some list of mutual avoidances between the different pieces. And maybe I'll write down just what that list is, but then I'm going to stop. So it would be 1, 2, 3, 4, 3, 4, 5, and 5, 6. So you have to keep track of these things. So you can continue now. This would represent a number of self-avoiding walks that go from some location y to some location x, interacting with the rest of the diagram. If you turn off that interaction and then look at the correction, you would free up this self-avoiding walk and give a factor equal to Cn minus m of x minus y, where n minus m is the length of this piece and y is wherever that happened to be. So what this leads to is this convolution equation here, star, with pi m of y equal to all of these contributions. Let me get some colored chalk here. It's these contributions after this tail has been cut off, leading to this factor Cn minus m of x minus y. So it's these guys. And the next time we go along, it will be this one. And you just carry on with this. So the signs are coming in an alternating way because of the inclusion-exclusion. There was a minus sign here that will affect this term. And then there's 2 minus signs by the time we get to this term. So it's inclusion-exclusion. So you end up with an alternating sum. And here the avoidances are 1, 2, 3, 4, and 3, 4, 5, and so on. So, pardon me? Yeah, thank you. So let me just say what these diagrams actually mean. This is simply the number of self-avoiding returns that take m steps. So it's the number of self-avoiding walks of length m that start at 0 and come back to 0. So they're not self-avoiding in the sense that they close at the end, but otherwise they are. Okay, so that's the meaning of this. It's a combinatorial object. It's just counting the number of walks that have this particular topology. This is a similar thing. It's the number of theta diagrams or 2-loop diagrams. These are walks which take m steps. We want to count how many there are that take m steps, start at 0, go to y, go back to 0, and then go to y, and are otherwise self-avoiding except for those intersections that are explicitly prescribed in the picture. As you move along, it starts to get a little bit more complicated. The walk is being instructed to do more and more unlikely things, actually. So here it has to go, start at 0, do a self-avoiding return, and then visit some place that it was along the return, and then visit some place that it was when it was returning to the return. And it needs to do that in such a way that various mutual avoidances are obeyed. You want to count how many walks do that. That's what the meaning of this term. And they go on. So there are more and more terms, and we're interested in actually what happens for m arbitrarily large. So this is becoming an infinite series in that limit. When we go to generating functions, we'll have to look at infinite series. So you should think about this as an alternating series that goes on forever. For any finite m, it will terminate. But when you increase m, you'll have more and more terms. So that's the Lace expansion. Now, as I said, when Bridges and Spencer did this, it was more in the form of a calculation where you write the self-avoidance interaction as a product over pairs of times 1 plus UST, like I did in the first lecture, and then you expand out that product and you do a resummation. The resummation, there's the notions of connected graphs and special classes of minimally connected graphs called laces. All of that kind of structure means that you can write an equation for pi m of y rather than, with the right-hand side just in terms of sums and products instead of these pictures. But ultimately, you're going to want to draw these pictures anyway because they're really telling you what's going on. So this is a shortcut. But if you have any question about what it means, then this is a good time to ask because I'm going to be building on this. The 1, 2, 3, 4. No, that's right. I'm about to forget it. I'm going to forget it. If you want to go down to d equals 5, then you should remember some of it. Okay? But you're right that we are going to ignore this information in our discussion because we won't need it. However, if you want to write an identity, then you do need it. Yes? No, they don't get more complicated. So if you want to, they look like this. They have a simple structure. And then the pattern is 4. So it will be 1, 2, 3, 4. And then 2, 3. I don't remember, actually. It's 2, 3, 4, 5, or is it 3, 4, 5, 6? I don't remember. But they come in groups of 4, and then the last one has a group of 3. So it's, there's a nice pattern, and the diagrams have a nice structure, which is important because actually we have to do estimates on all of these terms. And the fact that they have this kind of structure, which is just growing in sort of a ladder, makes it possible to continue. Yes? No. No, we're not interested ever in truncating this. Yeah, we want to go right up to the critical point. And if you start using, well, you have to be very careful about inequalities when you go all the way to the critical point. So we don't want to do that. Yes? This tail here. Yeah, that's right. So I keep on going until there's no more tail. You see, I mean, eventually this is a finite walk. So at a certain point, there's no more tail. And that corresponds to the term m equals n in this sum. Okay, it's a zero-step walk, the zero-step tail. That will eventually happen just because our walk has length m and it can only tie itself up so many times. So this is an alternating series, and I'll write it as the sum n equals 1 to infinity minus 1 to the n pi m n of y. So n is counting the number of loops. There's a 1-loop diagram, 2-loop diagram, 3-loop diagram, and then there's a 1, 2, 3, 4, 5, 6, 7-loop diagram shown there, and we get them all. And they all look like this. All right, so we have an equation, this convolution equation. It's a convolution in space. It's a convolution in time. And we know what these coefficients pi are. It's this alternating series of numbers of walks of specific topologies. So we want to analyze it. Well, you know, a convolution is a kind of product, and it's nicer to have products of real numbers just multiplied together instead of having convolutions, which are complicated things. And so we can use transforms in order to turn this convolution equation into something simpler. And the first transform that I want to use is a generating function, which is just a kind of Laplace transform. So here's a basic fact about generating functions that I'm sure that you're familiar with. That if I have two generating functions, a of z, which is this generating function with coefficients an, and b of z, not the bubble diagram here, this is just some generating function with coefficients bn, then the product a of z, b of z is equal to the sum n equals 0 to infinity cn zn, where cn is the convolution of a and b. So when you go to generating functions, convolutions of sequences turn into products of generating functions. So that's very nice. And anyway, we're interested in the generating function for Cn of x. We're interested in the bubble diagram, which is the L2 norm squared of gz of x, which is the generating function for Cn of x. So it's very natural at this point to go to generating functions. Multiply this equation by z to the n and sum over n. And as always happens when you do that, you have to pay some attention to what's going on for n equals 0, or you're going to end up with a real mess. So let's go to generating functions. Gz of x, by definition, is this series. And that equation over there is not good if n equals 0. So I want to extract from this the n equals 0 term, which has z to the 0, 1, and C0 of x is just the Kronecker delta 0x. N equals 1 to infinity Cn of x z to the n. And now n is at least 1, so I can substitute in the equation over there. And what will happen is that the convolutions in time will turn into products of generating functions. The convolution in space will remain. I don't like that either. We'll have to get rid of that too, but that'll be later. So this becomes delta 0x plus, there's the C1 term, which I want to have with a z beside it. So there'll be a z sum over y, C1 of y, times gz of x minus y. That's what you get from substituting the first term into here. And then for the second term, we'll have the sum over y of pi z of y, that's a capital Pi, times gz of x minus y, where pi z of y is the generating function for our sequence pi n. Okay, so all I'm saying is that the convolutions in time over there turn into products of generating functions. There was also a convolution in space, and it's still sitting here. Well, the convolution in space is, can be handled with the Fourier transform. So if we take a Fourier transform, which is just kind of a multidimensional generating function, so if I have a function f on zd going into to R or into C, doesn't matter, that's absolutely summable, then we can define its Fourier transform, f hat of k is the sum over x in zd of f of x times e to the I k dot x. That's the Kronecker delta there, and k would be in the dual of zd, which is minus pi pi to the d. So k is a vector with components k1 up to kd, each component between minus pi and plus pi. It's living in the torus. And that's the definition of the Fourier transform of this absolutely summable function f. And then it has the property that if you take the convolution of f and g, so I'll just define what that is, sum over y, f of y, g of x minus y, has the property that its Fourier transform is equal to the product of the Fourier transforms. It's the same fact as over here, except multidimensional. So now what we can do is we can take these convolutions in space and convert them into convolutions in time, into products, I should say. So I want to take the Fourier transform of this equation. Then I won't have any convolutions left at all. In fact, I'll just have a linear equation for the Fourier transform of the two-point function that I'll be able to solve. So we get gz hat of k. Fourier transform of the delta function is 1. Then I'll have plus z c1 hat of k times gz hat of k plus pi z hat of k times gz hat of k. That's just a linear equation for gz hat, and I can solve it. Take the two terms on the right-hand side over to the other side. They come in with minuses, and then divide by the common factor. And so what that leads to is that gz hat of k is equal to 1 over 1 minus z c1 hat of k minus pi hat z of k. You could solve this equation if you wanted for pi z hat of k, and that would write pi z hat of k in terms of gz hat of k. And this is the reason why I claimed that it was possible to determine the coefficients pi m of y in terms of the Cn of x's. That the equation that I wrote down that the Lace expansion sort of explains always has a solution, but what's useful is that we have a nice expression for what that solution is. We know what pi is. Now, this is a very explicit object here, this c1 hat of k. I'd like to work it out a little bit. So this is equal to the sum over y of c1 of y times e to the I k dot y. We're talking, so then let me divide this by the cardinality of the step set. That would just be 2d if we were talking about the nearest neighbor model, or for the spread out model it would be something bigger, and then multiply by that same quantity. And then what this is the one-step distribution for the underlying simple random walk. It's the probability that a simple random walk will go in one step to y. The c1 of y would be 1 if y is within range of one step, and then you're dividing by the number of places that you could have gone. And so I'm going to give this a name, call it d of y. And let's just write down what its Fourier transform is for the nearest neighbor model. So for the nearest neighbor model, so this becomes omega d hat of k. D hat of k, what's it going to be? It's 1 over 2d, that's the cardinality of the step set, times the sum over the nearest neighbors of the origin. Now the nearest neighbors of the origin, they come in two flavors. There's the plus type and the minus type. So I'll have j equals 1 up to d of e to the I. And then I take the dot product of k with a neighbor of the origin. What that does is it just picks off the coefficient of the component of k corresponding to that neighbor. So I'll have kj and then also a minus kj. Okay, it's a very explicit computation, and of course when you add up those exponentials you end up with a cosine. And so this is 1 over d times the sum j equals 1 up to d of the cosine of kj, kj being the components of this vector k which has d components between minus pi and plus pi. So this first term is something which is extremely explicit. And in fact, if you were to erase the pi, then you would be staring at the green function for simple random walk expressed in terms of its Fourier transform. All right, so let me rewrite this equation in the form that I'm going to want it. Gz hat of k is equal to 1 over 1 minus z times the cardinality d hat of k minus pi z hat of k. And this is the equation that we need to study. Now, one observation that we should make at this point is that the value of k equals 0 is particularly interesting. Because when you take a Fourier transform with k equals 0, that's just the L1 norm. Well, not the L1 norm, but just the sum. We're talking about something positive here, so it's going to be the L1 norm. So the exponential is not there when k is equal to 0. So Gz hat of 0 is equal to the sum over x of Gz of x, definition of the Fourier transform, and that's the sum over x of the sum over n of Cn of x times z to the n. N goes from 0 to infinity. You interchange the sums, then you forget where the walk ends, and the sum over x of Cn of x is just Cn. So this is the sum over n of Cn times z to the n, and that's the susceptibility. So the Fourier transform of the 2-point function is just equal to the susceptibility when k is equal to 0. And the susceptibility is blowing up at k equals 0 when z goes to zc. So let's recall what it is that we were trying to do. Our goal was to show that the critical bubble diagram is finite. Let's express the critical bubble diagram, or the bubble diagram in general, in terms of this Fourier transform of the 2-point function. So b of z, by definition, was the sum over x of Gz of x squared. It's the L2 norm squared of Gz of x. But there's this Parseval relation that expresses the L2 norm of a function in terms of the L2 norm of the Fourier transform. In fact, they're the same. So this is equal to the L2 norm of the Fourier transform of G squared. But that L2 norm is given in terms of an integral rather than a sum. So you integrate over minus pi pi to the d, Gz hat of k squared dk. That's a d-dimensional Lebesgue integration, normalized by dividing by 2 pi to the d. So this is just the Parseval relation. And so the way that we are going to approach showing that the critical bubble diagram is finite is via investigating the L2 norm squared of the Fourier transform of the 2-point function, which is just as good as looking at the original L2 norm because of this identity. Now, what makes this tricky is that this chi z is going to infinity as z approaches zc. And we're interested in what happens at zc. And so this is an improper integral once we get to z equals zc, because there's a 0 squared in the denominator of the integrand. So this is an improper integral when z equals zc, because gzc hat of 0 is equal to infinity. And so the question boils down to whether that improper integral converges or diverges. And there should be an issue here because we don't expect the bubble diagram to be finite in low dimensions because gamma is not equal to 1. So somehow the dimension has to come into verifying the integrability of this function. All right, so I want to make some observations here. First one is that you can understand the critical point in terms of this function pi rather nicely. So when k is equal to 0, this is the susceptibility, which is going to infinity as z approaches zc. The numerator is 1, so the way that it's going to infinity is because the denominator goes to 0. So if we put k equals 0 and z equals zc, this denominator should be equal to 0. That is characterizing the critical point. Yeah? Yes? Yeah, so you don't know that yet. But you know that you have to be worried at least there. Later we'll see that this is your only concern. So the critical point obeys the equation which says that put k equals 0, z equals zc, then the denominator has to be equal to 0. So 0 is chi zc inverse, which is the denominator, 1 minus zc. And you know, this d was normalized into a probability measure, so its characteristic function, which is what the Fourier transform is equal to 1 at k equals 0. So it doesn't show up. And you can solve this equation, well, at least you can isolate the zc. So you get that zc is equal to 1 over omega times 1 minus, 1 minus or 1 plus? This is, yeah, this is, let's see, minus. And so you can try to solve this equation in an iterative way, say in terms of powers of 1 over the dimension. That's, I mentioned the existence of a asymptotic expansion in powers of 1 over d for the connective constant. This is its reciprocal. It also has such an expansion. And that's proved by examining this equation. Once you know something about the convergence properties of this pi, which we don't know so far in this lecture, but we'll discover in due course. And in fact, in the tutorial tomorrow, one of the problems that will be worked out will be showing how to compute the first 3 terms in the 1 over d expansion for the critical point using this formula. So you get some information about the critical point once you understand pi. Second thing is that pi hat z, actually before I come to that, I guess before I was a bit premature with these notes. So I want to rewrite the equation for the Fourier transform of the 2-point function before making the next note. So let's do that. So I'll write gz hat of k equals 1 over fz hat of k. The reciprocal of g hat is much more interesting than g hat. So in a way, I mean, that's where the action is. The numerator is 1. So let's study the denominator, call it f. And then I'm going to write this as 1 over f hat of 0 plus f hat of k minus f hat of 0, which I can do. F is just the denominator. It's got 3 terms in it, and so I can see what this becomes. The first term is just the denominator in the value at k equals 0, which is the susceptibility. So this first term, f hat z of 0, is the reciprocal of the susceptibility. That's something which is going to 0 as z approaches zc. So it's going to disappear when we get to the critical point. Then when I look at this difference, there'll be two contributions. There'll be the difference between this term at k and at k equals 0, and the difference between this term at k and at k equals 0. And the d hat of 0 is 1. So I'll have z times omega times 1 minus d hat of k plus pi hat of 0 minus pi hat of k. Now, if the pi were not present, this would just be something which shows up when you're studying simple random walks. I mean, pi equals 0 gives a simple random walk. And so this is a simple random walk quantity which is showing up. This is the modification to it. And we want, basically, the proof boils down to showing that when d is bigger than 4, this term is a small adjustment to this term. So we are going to need to really understand what this term looks like. And that's where the second note comes in. So pi hat z of 0 minus pi hat z of k, by definition of the Fourier transform, is the sum over x of 1 minus e to the I k dot x times pi z of x. Now, we have some symmetry going here between x and minus x. And so if you make use of that, then this exponential turns into a cosine. So this is the sum over x of 1 minus the cosine of k dot x times pi z of x. So this is something that we need to study. And the third note is to look in some detail at what this is, because in a way what we want to do is we want to compare this thing from note 2 to 1 minus d hat of k. So let's take a look at 1 minus d hat of k. Let's just do it for the nearest neighbor model now. It's a little more complicated if you want to look at spread out model, but it's always explicit and it's not a problem. But let's just look at the case where we calculated d hat of k as that normalized sum of the cosines of the components of k. And then we'll put 1 inside that sum as well. It's a normalized sum. So this is the sum j equals 1 up to d of 1 minus the cosine of k of j, something related to the inverse Laplacian. Or, well, the Laplacian, but it's in the denominator, so it becomes an inverse. And if we look at how this behaves as k goes to 0, which is the place that we were kind of had our eye out about, what will happen is that we're essentially looking at the behavior of this cosine near k equals 0, which behaves like 1 minus kj squared over 2. And so if we just look at that leading behavior, what we'll end up with is the norm of k squared divided by 2d as k goes to 0. And here already we see some sign that 4 dimensions is special. Because if you just forget about the pi and pretended that your Fourier transform of the 2-point function was just the part that comes from 1 minus d hat, the constant term is going to disappear at the critical point and be gone. It'll be 0. So it's just this part that's left. That's behaving like k squared. And we're interested in the L2 norm. So we have to integrate the square of k squared. And if you integrate the square of k squared in d dimensions near k equals 0, then you better have d greater than 4. So this will be finite if and only if d is greater than 4. All right. So if we want to do anything with this approach, it's necessary really for us to understand the effect of this term. This part's explicit. We know everything about it. No problem. This part, more mysterious. This pi hat of k is the Fourier transform of the generating function of that alternating series that arose out of inclusion-exclusion of coefficients which are counting self-avoiding walks that are constrained to obey certain rules about how they intersect themselves and don't intersect themselves and so on. So we have to do some estimates in order to get anywhere now. So we call these diagrammatic estimates because we're thinking about pi really as being expressed in terms of diagrams, and we want to get some control over these diagrams in the form of upper bounds. So let's recall what the definitions are. So pi z of x is the generating function for a sequence which was written in terms of alternating terms. And so we can write the generating function also as an alternating series of generating functions. Where pi z n of x is just equal to the sum from m equals 2 to infinity of minus 1 to the n pi m n of x. That's a small pi on the right-hand side. So that's the thing which is counting the number of n loop diagrams of m steps that go from 0 to x. And there's a z to the m. All right, so that's the x-space version of this Fourier transform, which is appearing here. And I'll remind you what these coefficients look like. So pi m1 of x was equal to the number of these things. Pi m2 of x is equal to the number of these things, taking m steps. Pi m3, these things. And I'll draw one more. For loop diagram looks like that. And oh, yeah, thank you. I want this to be non-negative for each n. The signs are taken into account here. Thanks very much. Now, there's the self-avoidances between the different parts of the diagram, which we could keep track of as if we wanted to, but as Greg pointed out, we don't want to. So let's not. They're there if you want, but we're going to forget about them. And we'll see why. It's because we're interested in upper bounds on these terms. And in upper bounds, it's fine if we forget about the fact that two pieces have to avoid each other. Okay, so there's a repulsive nature to this interaction, which is actually crucial for applying the analysis. If we had, like Frank has been talking about, a walk that had a nearest neighbor, self-avoiding walk with nearest neighbor attraction, then we would not be able to forget about the interaction between the two pieces. And this method actually fails in that setting, except in a special case that was studied by Daniel Ulci, where you had to do something fancy. So I'm going to not keep track of that list because we're going to forget about it in an upper bound. But there's one thing that I do want to keep track of, which is which one of these subwalks is allowed to take 0 steps. And if you keep track of that, it's this one, and this one, and this one. It's all the horizontal ones as you extend the ladder. So that little mark there is there to indicate that it's possible that that walk actually takes no steps, but all of the other walks actually have to do something. So you have to go back to the derivation of the Lace expansion to see why this is the case. But if you do go back, then that's what you'll find. Now, I want to define h z of x to be the generating function which doesn't consider the possibility of no steps. So this is the generating function for Cn of x, but I'm leaving out the n equals 0 term. So if you like, it's gz of x minus delta 0x, which is just the n equals 0 term inside the generating function gz of x. So I'm kicking that one out and calling the result h. I don't like that delta 0x very much because sometimes it's 1, and I want small factors appearing in my upper bounds, and I don't want 1 plus a small factor. And so it's actually important to keep track of that. And here's the theorem. For any z greater than 0, the following estimates hold. Sum over x pi z1 of x, n equals 1 is a little bit special, is bounded above by z times the cardinality of the step set times the L infinity norm of h. And for higher values of n, the estimate looks a little bit different. There's an infinity norm of h, and then there's an infinity norm of the convolution of g and h raised to the power n minus 2, n minus 1, for n greater than or equal to 2. We're also interested in this quantity. As I pointed out, this pi hat 0 minus pi hat of k is something that we need to compare with the k squared term, the 1 minus d hat of k. So we need estimates on that as well. So the sum over x of 1 minus cosine k dot x times pi n of x is bounded above by, well, it's just plain 0 if n is equal to 1. And otherwise, it's bounded above by n squared times the L infinity norm of 1 minus cos k dot x times hz times this same gz star hz infinity norm raised to a power which is, again, n minus 1. Pardon me? Star is the convolution in x space. Yeah, so g and h are functions of x, and we take the convolution in x space. Sum over y, g of y times h of x minus y. All right, so I don't want to prove this theorem in, for all the different values of n. But let's just prove it for n equals 2. Before I get into that, I mean, this 0 is trivial because when n is equal to 1, there's this delta function, which is showing up in the n equals 1 term. This is really a delta function at x. And so when you have a delta function at x, then the cosine is going to be 1. At x equals 0, a delta x 0. That'll set x equal to 0. The cosine becomes 1, and there's a cancellation. So this just follows from the definition of pi 1. So let's look at the proof for n equals 2. OK, so here's our pi, pi m2, and that's going into this generating function. So pi m2 of x is equal to the number of m-step walks that look like this. And now I'll make explicit the fact that the walks are supposed to be avoiding each other, but in an upper bound, we can forget about that. So now you're supposed to think about these walks as no longer having the constraint that they need to mutually avoid each other. They're still self-avoiding walks. The total length is m, and there are 3 of them. So if we go to generating functions now, and we sum over x, so I hope you can tell my generating functions from the coefficients, but the subscript should help. If it's a z, it's a generating function. If it's an m, it's the coefficient. So now we're taking a generating function. So we're summing this thing over m, multiplying by z to the m. The total length is m, so we can take the factor z to the m and associate a z to the length of this bit times z to the length of that bit times z to the length of that bit, and end up with a product of 3 generating functions. This is just like a big convolution in time that turns into a product of generating functions. Once we've forgotten about the interaction, the pieces are independent of each other. So this is bounded above by the sum over x of the generating function of these pieces, and each of these pieces is required to take at least one step. So we have hz of x cubed. And now the bound is easy, because this is just take out a factor, the worst thing that one of those hz of x's can be. That's the L infinity norm, and taking the supremum or the maximum over x of one of those factors. And then what I have left is the sum over x of hz of x. And actually, h is symmetric, so I can write hz of minus x for the other factor, and it won't change anything. And this is just the convolution at 0. Which is bounded by the supremum over x of the convolution at x. So this is bounded by the infinity norm of h times the infinity norm of the convolution of h with itself. And h is less than g, and everything's positive, so I don't need to worry about absolute values, and I can replace one of those h's in the convolution by g. I'm giving something away there, and maybe I would want to do that, but I just went ahead and did it. How does it work in this case? Same thing. What's different is that there's a factor of 1 minus cosine of x multiplying here. That's non-negative. So it survives in this bound, 1 minus cosine of k dot x. And so it's going to also be sitting in here. And I'll just pull it out when I take the supremum. I'll put it with the h. When I take the supremum, I'll take out the worst case of 1 minus cosine k dot x times h. And that will give me this factor. And then I'll have g star h to the 1 left over. And, well, I won't see the n squared until I go higher. OK? Yeah, so there's no marked leg here. There's no marked line here. And so marked lines correspond to g's, because they're allowed to have, they have the 0-step contribution, and the unmarked lines correspond to h. So it's a happy situation here that nobody's marked, so that's good news, because in our upper bound, h is smaller than g. You know, g has a 1 in it, and we would not be happy to have g here rather than h, because if we had g, then this would be a factor 1. zc times omega turns out to be of order 1. And this would be saying that pi 1 is of order 1. That's no good. We want it to be small. So we cannot tolerate having a 1 here. OK, so we have these bounds. You have to do a little bit of work in order to generalize to other ends. But let me just draw you a picture that shows you why you should be able to do that. How would the bound go here? You just break up the picture into like that. And you get infinity norm of h, infinity norm of h star g, infinity norm of h star g, infinity norm of h star h. That's why you end up with a geometric series. So, well, you probably have to think about that a little bit in order to consider it a proof. But that's how you prove it. So what are you going to do with these bounds? It looks like we have not made terribly much progress, because let me show you something. Suppose we use the Cauchy-Schwarz inequality now to bound this infinity norm of the convolution. So h star h, for example, infinity norm. That's the sum over x of h of x times h of minus x. Apply the Cauchy-Schwarz inequality to that. And then what you'll bound it above by is the L2 norm squared of h. And, well, let's give away the 1. That would be bounded above by the L2 norm squared of g, which is the bubble diagram. So at this point, it would be reasonable to fall into deep despair because you would say, I'm trying to show that the bubble diagram is finite. And what I've done is I've told you a somewhat long story about how you can take the two-point function and express it in terms of this pi, which is supposed to be helping you to show that the bubble diagram is finite. But now I'm telling you that when you estimate pi, you find out that the upper bound that you get on pi is the bubble diagram, which is the thing that you wanted to show was finite in the first place. And so you feel some concern. Of course, there's a way around this. And that is really what is going to be the topic of the lecture next time. So I see that my time is just about up, so perhaps I shouldn't say very much more right now. I won't go into any detail. But one thing I should say is that what I've told you today is very specific to the self-avoiding walk, in the sense that this expansion that we've derived was very dependent on the fact that we were talking about self-avoiding walks. We used inclusion-exclusion in a very specific way. We ended up with these diagrams which are representing the pi. Those diagrams are specific to self-avoiding walk. What happens next, the analysis that happens next, is more general, however. So in order to explain that, let me say that if you were to do this procedure for percolation, so it's possible to apply a similar expansion in percolation, to derive a similar expansion based on inclusion-exclusion, which I'm not going to explain here, but it looks rather different than what we've seen today. The percolation is not the same as self-avoiding walks, and you have to pay attention to the fact that you're dealing with a different model when you work out what the expansion gives you. However, what will happen is that you'll end up with an equation for the Fourier transform of the two-point function, which in percolation is the probability that 2 points are in the same cluster, that has this same form. There's a numerator in that case, but the denominator is the same. It's 1 minus z times omega d hat of k minus some pi hat of k, where pi hat of k is in terms of some diagrams which are not these diagrams. They're bounded not in terms of the bubble diagram like what we have here, but you need a triangle diagram in order to bound those. So that whole story kind of moves in parallel for percolation to self-avoiding walk, but it's different. However, once you reach the stage that we're at now, if I took another lecture and went through the whole thing for percolation, I would be at the same point that I am now with a formula for the Fourier transform of the two-point function, diagrammatic estimates on the pi that arises, and then the analysis from that point on becomes the same for percolation or for self-avoiding walks. So I'll do that analysis tomorrow for the case of self-avoiding walks. Thank you. Yeah, so the question is, can you do this for the Ising model? Yes. So about 5 years ago, Akira Sakai found a version of the expansion that works for the Ising model. It's based on random current representation for the Ising model. And it does apply, yes.
I have another announcement for participants of Brazilian School of Probability, especially Brazilians. So tomorrow, after second lecture of Rick Kenyon, at 8:45, we will hold our traditional assembly for discussing issues for the future, so everyone is very much welcome, so it will not take long before going to the party. So tomorrow, 8:45, assembly of Brazilian participants of this school. So I will tell it in Portuguese once again. So para todos os participantes brasileiros, amanhã nós vamos ter nossa tradicional assembleia do comunidade para discutir assuntos de futuro às 8:45, depois de palestra do Rick Kenyon. Todo mundo bem-vindo. Obrigado.